All right, so in this fourth lecture, I would like to talk about what is it from a mathematical viewpoint that you need to do for a finite element code. So if we look at the finite element method from a mathematical viewpoint, then there are a number of building blocks that we somehow have to, let's say, realize in code, that we have to implement. And I would like to go through, let's say, the mathematics first, and identify what are the concepts, and then we come back to how to implement these building blocks in our code. So the fourth lecture will be the building blocks of a finite element code. Okay, so let me start this from a mathematical perspective, and I'm going to use the very simplest partial differential equation you can think of, which is just the Poisson equation, or the Laplace equation if you want to. So the Laplace equation, I'm going to use these terms interchangeably. Poisson equation really should be the Laplace equation with a non-zero right-hand side, whereas the Laplace equation would be the one where I have a zero right-hand side, but people use these terms interchangeably. So forgive me if I use the wrong term. So we're going to look at this equation, minus Laplace u equals f in the domain, and then for simplicity I'm going to impose zero boundary conditions all around. And I'll show you later in the actual code how to do this in a more general way, so that you can impose something that is non-zero, or you can impose different kinds of boundary conditions, like Neumann boundary conditions, for example. But let's start with this one here. So we learned from, let's say, the theory of partial differential equations that these sort of equations don't necessarily seem to have an equation, a solution. So you think that just because I have second derivatives in the Laplace operator here, that the solution needs to have second derivatives at every single point. But that turns out not to be true. I can find examples where I impose even a very simple right-hand side, let's say f equals 1, in a domain that has, for example, a crack or a re-entrant corner. And it turns out that for these sort of cases, with this domain and with this right-hand side, that there is no function u for which pointwise the second derivative exists or equals f. So people a long time ago, let's say in the 1910s, 20s, 30s or so, figured out that this particular formulation of the Laplace equation does not necessarily have a solution. And so they found how to reformulate it in such a way that we can always talk about what it is that, let's say, so that we can talk about that there is always a solution, and in particular, what sort of properties the solution has to satisfy. And the way this works is that we say, well, let's say ideally we would want to be that minus Laplace u equals f, and when we say that the left and the right hand side are equal, what we really mean by that, of course, is that this needs to be the case at every single point. And like I say, it's not possible to satisfy this. But let's presume that it was true. Then I could certainly multiply both sides of this equation with another function that we call a test function, and integrate over the entire domain. So if I do this, then I get something that is called the weak formulation. And when I say parenthesis grad phi comma grad u parenthesis, what I mean by this is that this is the integral over omega of gradient phi dot gradient u dx. Okay? Which is, of course, exactly the same as the left-hand side up there multiplied by a function just after integrating by parts. And so if the left and the right-hand side of the strong form up here are the same, then of course these two sides of this equation must be the same for any possible test function phi, right? Yeah. That's sort of the essence of asking that the top equation is satisfied in a pointwise sense. So the weak form would say, I'm looking for a function u in such a way that gradient phi comma gradient u equals phi comma f for any test function phi. That turns out to be a problem that always has a solution if I ask the question in the sense of saying it must be true for any test function phi in a particular set of functions. In particular, for all of the functions that are in this function space h1. Okay? So if I do this, then there is a function u of x in an infinite dimensional function space, namely in this particular case h1 or h10, that satisfies this equation. And that's the starting point of the finite element method. I should point out one thing. So oftentimes when we do mathematical theory, we multiply with this test function from the right. So instead of saying gradient phi, gradient u, we say gradient u, gradient phi, which of course is exactly the same thing, because both of them are just integral gradient phi, gradient u, or integral gradient u, gradient phi. I can exchange these sort of things. It's the same object, it's the same number that we get. But I have come to, let's say, have a habit of always multiplying from the left, and you will see at a later time why that is a habit that's very useful. It's one of the many little tricks that you can use if you want to avoid, let's say, common programming errors. If you always multiply from the left, you will find that you always come out with the right matrix, whereas if you multiply from the right with this test function phi, then you will find that you come out with the transpose of the matrix. And of course, if you keep track of where you need the matrix or the transpose of the matrix, then everything is fine. But it is a lot easier to get it right if you get in the habit of always multiplying from the left. So there is no mathematical meaning behind it, it's just a trick to make it easier on you to implement stuff. Okay, so we're at the weak formulation, gradient phi, gradient u equals phi comma f for every test function phi. And then the question is, well, how do we do this? Now, we know that this u of x is from an infinite dimensional function space. So it's a function, for example, that could have a different value at every single point in the domain. And there are, of course, infinitely many points in a domain. And the consequence is that if you have infinitely many points, then that means that, well, your computer will have a lot of work to do, right? Because computing the values at infinitely many points is going to take clearly a very long time. And since computers are not particularly good at computing things infinitely often, we need to find a way to make this a finite number. And the idea of the finite element method, or actually of many other methods too, is that we want to approximate this function u of x by a function ua of x that we write as a linear combination of phi j's of x. Namely, I want to write this approximation uh as a sum from j equals 1 to n of coefficients, these are just numbers, uj, times functions phi j of x, where for now it's just assumed that I have these functions phi j given. Somebody gave me these functions phi j of x, and I would like to find a function uh that I can write as a sum of coefficients uj times these phi j of x. I don't know these coefficients uj right now, and of course my goal is going to be that I determine these values uj in such a way that this function comes as close as possible to the solution u of the original PDE, right? That's the goal of it. Now, if I do this, let's say if I put this function so defined into this weak form, grad phi grad u equals phi comma f, then the weak form says that this has to be true for every test function phi. In other words, these are infinitely many equations that I have there, right? I have infinitely many test functions phi. That gives me infinitely many equations that need to be satisfied. And it's quite clear that if I put this so defined into this equation, that's not going to work, because I only have n coefficients, but I have n coefficients, but infinitely many equations. And that is too many equations for just not enough coefficients. So what I need to come up with is a way to select exactly n equations out of these infinitely many, right? And the way we do this is that we put this into this weak form, and we require that gradient phi gradient equals phi comma f, not for all possible phi's, but only for exactly those n functions phi I. Okay, so that gives me n equations for n coefficients. That is the fundamental basis of the finite element method, and it is called a Galerkin approach, or a Galerkin method, to do it this way. So if these functions phi I are linearly independent, then this gives me n equations for n coefficients, and hopefully that is of course enough. There are cases, let's say for the Laplace equation, it works out. There are cases for other equations where it's not quite so easy, where I need to have additional conditions on these functions phi I. But for the Laplace equation, that is the simplest way to do it. So I would like to add one more thing. So oftentimes, again in the mathematical literature, we write UH equals not the sum over j from 1 to n, but the sum over I from 1 to n, ui phi I of x, which is of course exactly the same object, because we sum over this index I or j. It's a silent index. It appears only under the sum. But it is convenient if you write it as a sum over j, because if you do it this way, so we take this object here, we plug it into here, then I have something over here on the left that is something like something with I times a sum over j, and that will turn out to be exactly the way I need to write this as a linear system. I could of course have used the index I over here and the index j over here, but that again leads to the transpose of the matrix I really want. So it turns out to be convenient if you get again in the habit of using the index j in this place up here, and the test function to call it phi I. All right, so the practical question number one, of course, is how do you define these functions phi I? And that is something that we do in the finite element method in a very particular way. Namely, we take our domain and we subdivide it into what we call cells. So we take the domain, we split it into triangles or quadrilaterals, for example, or in 3D into tetrahedra or hexahedra or prisms or pyramids. And we call these things cells, and then the mesh is a collection of cells. And each one of these cells that we have is something that we map from what we call a reference cell. And then we define these basis functions on the reference cell, and the real functions phi I and phi j. These are the mappings of the shape functions defined on the reference cell. So let me give you a graphical illustration of this. Let's say the domain that we want to solve our equation on omega is this, I don't know, potato-shaped thing here on the left. We subdivide, or we approximate this domain by a collection of triangles. So the thing on the right would be a mesh. It consists of a number of triangles, and each one of these triangles is a mapping, a transformation of a reference cell, which is the reference triangle in this case, which would go from x equals 0 to x equals 1, and from y equals 0 to y equals 1. And then there is a linear mapping in this particular case to rotate and stretch this triangle into this one over here. So each one of the triangles, each one of the cells of my mesh is a mapping of the reference cell. What do we do with this then? So the next step would be that we define our finite element. And the finite element in this particular case would be something down here. So up there, the reference cell is a geometric entity. Down here we have degrees of freedom. These are where these are the definitions of the shape functions. So you've seen before how to define the P1 shape functions, for example. These would be one shape function per vertex of each triangle. And then what I need to do is I need to enumerate them on each individual cell. So we're programmers in C++, so we always start enumerating from 0. So on the reference cell it would be 0, 1, and 2, for example. But then we need to enumerate them globally as well, so that we can talk about a function space defined on omega. So I could, for example, enumerate 0, 1, 2, 3, 4, 5, and so on and so forth. So I need a global enumeration of all of the degrees of freedom. And so, for example, shape function phi 1 on this particular cell would equal this shape function mapped using this mapping onto this cell. On this cell, it would be one of the shape functions on another reference cell, again mapped to this particular cell. Okay. All right, so to come back to the things that we just did, we needed to define a mesh, we needed to define a mapping, we needed to define a reference cell, basis functions on the reference cell, we needed to enumerate the degrees of freedom on the global mesh. All of these things are things that we have identified in our mathematical formulation that are concepts, mathematical concepts that we somehow have to, let's say, implement or represent in our software. There are more concepts. So if you have this definition of how your approximation UH is defined, right, as the sum of uj phi j of x, and we put this in here, then so I take the sum, I put it in here, I can pull the sum out of this, and I get that this is the integral gradient phi I gradient phi j dx times uj, and the same over on the right hand side. This is exactly a linear system, namely there is a matrix A here, so this is the Aij entry of this matrix times this vector. So A times u, the ith row of A times u is exactly this, the left hand side of this equation. The ith row of this vector f is exactly the right hand side here of this equation. So I get a linear system, and in order to compute this matrix Aij, I need to ask, well, how would I compute this Aij in practice? Well, the way we do this is we say the ijth entry is gradient phi I gradient phi j. I compute this as a sum over all the cells. So I split this integral that I have here into an integral over all of the cells. So I get a sum over k. K are always the cells of my mesh, time of the integral over k of gradient phi I and gradient phi j on this particular cell. And then I can map these things. These things are defined, remember, on the reference cell, so I can map this back, right? So I get the gradient on the reference cell times the inverse of the Jacobian of this mapping for shape function phi I, the same thing for phi j here. But then if I integrate on the reference cell, I also get the determinant of the Jacobian of the mapping. So I get the absolute value of the determinant of the Jacobian of the mapping over here. This is how we always write down in practice the integration of a finite element term. And then, of course, these terms here, so typically we define these phi i's on the reference cell as polynomials, so the gradient is also a polynomial. The mapping is a polynomial. That means that the Jacobian is a polynomial. The inverse of the Jacobian is a matrix that consists of rational functions. And so typically, this whole thing here is a rational function, and we cannot typically integrate this exactly on a triangle or on a quadrilateral. So in order to compute this in practice, we use quadrature. So we replace this integral over the reference cell by a sum over quadrature points. And so we have to evaluate this whole integrand that we have here at quadrature points xq and sum over these, and then we get here the determinant and an additional factor. For example, we call this an integration weight for every quadrature point. So if we do this, you will find that there's a term, the determinant of j, of the Jacobian of the mapping, times these quadrature weights. It will turn out that in every single integration you will ever do in finite element methods, these two terms always appear together. The determinant of the Jacobian times the quadrature weight. And as a consequence, we have an abbreviation for this, jxw, for j times w. So whenever you see jxw in our software, in the code, it is always this term here. So you can think of this as a dx, right? So we will always write this as gradient phi I times gradient phi j times jxw. This is like the dx in the integration. This is what we do for the integration. So we have identified two more concepts, mapping and quadrature. We do this for the matrix. We do, of course, exactly the same thing for the right-hand side. Okay, so now we have a matrix A and a vector f, and we want to find the solution u of this. There are more concepts if you want to implement this in code. Namely, A is typically a sparse matrix, so you need to store it somehow. For example, if you don't want to store all of the elements of the entire matrix, what we use is a format that is called compressed row format. That means that we want to only store those entries in each row for this matrix that are non-zero. And similarly, you have these vectors u and f. These are simpler because every entry in these vectors is non-zero, so you can just store this as an array. Then you need to somehow have efficient algorithms that deal with, for example, the product between a matrix and a vector. And you need to deal with preconditioners for linear solvers. Of course, if you want to solve things in parallel, possibly on hundreds or thousands of processors, then you also need to have data structures and algorithms that can deal with the communication that comes with this, and so on and so forth. These are an additional set of concepts. Now we have this linear system. We also need to deal, of course, with solvers, either direct or iterative, maybe in parallel. And then once you have the solution from this, you need to think about, well, what is it that we actually want to do with the solution? So typically, you're not interested in just a bunch of numbers, but you want to do something. We just solved the PDE. Now we come back to the question why we solved this PDE, right? So you want to visualize the solution so that you can gain some, let's say, visual input of what the solution looks like, or maybe because you want to show the result to somebody who has an understanding of what it means. Or maybe we want to evaluate the quantities of interest. For example, if you're an airplane designer, you would want to compute the flow field around a wing so that you can compute the lift and the drag coefficients of this wing. These would be quantities of interest, these two numbers, the lift and the drag. Or you want to estimate the error, for example. So all of these things we collectively call post-processing the solution. So now we have a whole bunch of concepts. And there is a flowchart that essentially shows how these various different things mesh. So for example, we have the triangulation. The triangulation is the collection of all cells, so that's what we call the mesh. Triangulation, mesh is the same thing. Then we have a definition of the finite element. We have a definition of, let's say, the quadrature formula that we want to use. We need to define the mapping that we want to use to go from the reference cell to the real cell. If you have the collection of cells, so your mesh or your triangulation, and you know on the reference cell where the finite element shape functions are defined, then we needed to globally enumerate the degrees of freedom. This is something that we do in an object that we call DOF handler. DOF stands for degree of freedom. So the DOF handler is always the global enumeration of degrees of freedom. Then similarly, the finite element needs to be evaluated at quadrature points mapped from the reference to the real cell. That is something that an object called fvalues does. If you know how degrees of freedom are enumerated and you can compute integrals, then you can come out with these linear systems A u equals b, so you get a discrete system. And then you pass this on to the solver, and then from there to the post-processing. Now this is sort of the flow chart. I show you this because these different classes are represented in the documentation of deal.II. And we will come back to this later when I show you how the documentation of deal.II is represented. Essentially, each one of these boxes that I just identified is represented by something that we call a documentation module. So this is a collection of classes and functions that have something to do, for example, with a triangulation, or that have something to do with mappings. So this flowchart that I derived by going through the mathematics of how you would represent a finite element code is exactly what in the end shows up in the software. So to sum this up, if you go through the mathematics of the finite element method, you come out with a number of concepts that somehow need to be represented in a finite element code. And so we call these concepts and software components. So a concept is an abstract thing. A software component is something that implements this concept. Some of these concepts were purely come from the mathematics. Some other of these components come from what you actually want to do with the solution of a PDE. For example, if you want to evaluate it or visualize it, right? These are things that have nothing to do with the mathematics, but that are more to the point of, well, we solve a PDE for a particular purpose. And the next few lectures, essentially going through all of the tutorial programs that we have, we will go through individual ones of these components where we talk about individual components, for example, first for the triangulation, that would be step 1. For the DOF handler, that would be step 2. For the linear system, in step 3, and so on and so forth. So many of the lectures to come deal with individual ones of these components that we have just identified. So with this, we'll come back in the next lecture looking at step 1 and what that does.